Hello everyone. Today I am going to continue our discussion about dynamic programming. So as we have seen before, the idea of dynamic programming actually comes from the recursion and divide and conquer idea. That if you can find a good recursive relation for a problem and can store the solution for the subproblems and reuse it again, you can make your algorithm, your recursive algorithm, more efficient. For example, we started with the Fibonacci algorithm with this recursive relation that the nth number in the Fibonacci sequence is going to come from the nth minus 1 number and nth minus 2 number, the previous two numbers, right? So the idea of dynamic programming is that if you can have only polynomial number of subproblems, if you're solving a problem of size n and you can define only polynomial number of subproblems, by calculating all of them, the cost of calculating each one is going to be polynomial. So in total, the time complexity of your algorithm will be polynomial. So in the case of Fibonacci, it is clear that you have only n number of subproblems. Basically, each number in the sequence is going to be a subproblem, and you can store it in an array, and later on you can actually refer back to that. And the cost of using the previous subproblems to calculate the next one is polynomial. So in the case of Fibonacci, it was just adding the solution, the answer for the previous two subproblems. We have seen some other examples like the matrix multiplication, that in that case the number of subproblems that we had was n to n minus 1 divided by 2 subproblems. So basically we could actually save this one in a table. Remember, in the multiplication of the matrices, the subproblems was that if you are going to actually multiply n number of maybe I better adding more, a1, a2, a3, a4, and for example a5. So this is the main problem is of size n, and okay, then subproblems that you can have is going to be, for example, what is the best multiplication from a1 to an, what is the best multiplication from a2 to a5, what is the best way to multiply from a1 to a3, what is the best way to multiply from a2 to a4. So basically all of these choices that you started from some point and you end up at some other point in this sequence. You cannot actually change the order of the multiplications, right? The order of the matrices. It is just choosing which part of this sequence you are going to multiply. So these are all possible subproblems that you can have, and you can see that in this case, the number of subproblems that we have is going to be n to n minus 1 divided by 2, which is polynomial, of course. And to use the subproblems to get answer for the larger problem, we just need again O of n. So in total, the time complexity for us would be O of n power 3, and that's the reason dynamic programming can help us to solve this problem in polynomial time instead of exponential. If we don't reuse the subproblems, our algorithm will be exponential. Very similar problem like the Fibonacci. If we don't reuse the subproblems that we have actually calculated before, it can simply be an exponential algorithm, but we reuse them and it will be polynomial. So just again some recap from dynamic programming from the last session. When we can actually write our recursive algorithm and get the point that we can reuse the subproblems and solve the issue, we can start rewriting the whole algorithm instead of recursive way, instead of in a form of top-down way. We call that recursive way a top-down way. Instead of that, we can start rewriting it in a bottom-up way. So we can get rid of the recursion, rewrite the whole algorithm in a bottom-up way, in an iterative way. So you started calculating the solution for a smaller subproblem, and then at each step you actually go up and calculate the solution for the larger subproblem, larger, until you solve the original problem that you get of size, for example, n. And most of the time in the bottom-up way is going to be more efficient because you get rid of the recursion. We don't have the overhead of recursive calls. So it is more efficient to write your algorithm in bottom-up way. So today in this video, I'm going to discuss more problems. The problem I'm going to solve now is called weighted interval scheduling. So the problem statement is, assume we have n jobs, and each job is going to take some time, and basically I have an associated interval for that time. It means that it is important for me that the job should start at a specific time and should finish at some specific time. Okay, so it's not just the length of how much time it would take. We have some interval for that. It's important for me that it should be done in that specific slot of time. Okay, and for each job there is some weight associated to that. So the problem is I wanted to find the set of jobs that I can do without any conflict that maximize the summation of the weights. Okay, what does the conflict mean? So if you have a job that, for example, should start at, let's say time, for example, that a job should start at, for example, 12 p.m. and it will finish at 4 p.m., for example, and you have another job that should start at 2 p.m. and started at some other time, I don't know, for example 6, whatever. These two jobs are going to have conflict, right? You cannot do both of them. Either you are going to choose this job or this job. So the set of jobs that I wanted to choose is all of them should be compatible. There is no conflict between them. And there are many use cases for this problem. If you think about it, for example, just assume that I have a machine, a server, for example, and I wanted to get some jobs from outside. Some people are going to run their program or run their jobs on this machine, and there is going to be some specific time slot for each one, and they're going to pay me for their job. Okay, and I wanted to actually maximize the income, so I wanted to get find the set of jobs that there is no conflict, I can run all of them in my machine and maximize the income. So let me show you an example. Think about this set of jobs that basically I have, this is the number, these are the numbers, and I have some weighted associated to each one, and I have actually ordered these numbers, give them some number, and you can see the time slot in this diagram here. So what is the optimal answer for this example? I can give you the optimal answer by choosing these jobs. If I choose 12 and also choose 9, choose 6, 3 and 1. The weight of each one is 12 is 6, 8 is going to be 8, 9 is 8, and the job 6, the weight of that is 7, job 3, the weight is 10, and job 1, the weight is 5. So in total, these are the weights, this part. So in total, I'm going to have 36. Okay. This is the optimal. You may actually just try to find some other answers. This is the optimal answer that we can have for this example. But let's look at, think about some algorithms that we can apply to this problem. I'm going to review 2 examples of some algorithms that might come to mind to solve the problem. The first one is, be careful, this algorithm that I'm going to actually explain doesn't matter that I apply it from left, from the beginning, or I apply it from the end, but I'm going to apply it from the end. And what is the algorithm? The first one is saying that, okay, start from the last time that you are having a job, the finish time of the last job, and take if you are going to have more than one job at that finish at that time, you choose the one that has shortest length. The intuition here is that you're going to leave more time for the rest of the jobs, right? So for this algorithm, the first choice for me is, okay, it will choose 12, right? Then I cannot take any more job for this algorithm until this point, right? Until you reach to the beginning of the job 12. Now you can see that I am actually progressing I started from the end and going through to the beginning of the time. It doesn't really matter if you started from left, started with those jobs that started at the beginning, and apply the same idea. Choose the job that has the shortest length. So let's just continue this algorithm. Then the next job that I can take, again, I have 2 potential answers. I can take 10 and 9. Between these 2, 10 is going to be shorter, so I'm going to take 10. So the next job that I choose is 10. Again, the intuition is that you are going to leave more time for the rest of the jobs to choose. So after you reach the beginning of 10, okay, you can actually take some job. You cannot take 8, you cannot take 9. All of them are going to have conflict. The next job that you can actually take is going to be 6 or 7. So among these 2, the one which is shorter is going to be 6, so you choose 6. Then you can take any job until this point, and at this point you cannot choose 5, you cannot choose 7 anymore, you cannot choose 4, so the choice that I have is going to be 3, and I cannot take any job until here, and from this point it means I can't choose 2, but I can choose 1. So this is going to be the answer of this algorithm. What is the cost the weight associated to each one? It is going to be 6. Job 10 has weight 5. 6 is going to be 7, 10, and 5. Clearly, this is not going to give me the optimal answer here it is going to be 33. Okay, so you might actually argue that when you could choose between two jobs, you go with the shorter length instead of think about the costs. I mean, the thing that makes this algorithm complicated, this problem complicated, is that there are some costs associated to each job. So you cannot just think about the length of the jobs. And I mean, the intuition of this algorithm was always takes the job which is shorter, so it leaves more time for the rest of the jobs to choose. This algorithm basically is going to give me the optimal answer if the cost of all of the jobs were equal, right? So in that case, this algorithm, I can actually prove that this algorithm is going to give me the maximum number of jobs, because you don't care about the cost. I mean, all of them are going to pay the same amount of time. So this algorithm, the intuition is that this algorithm always chooses the shortest job and leaves more time for the rest of the jobs to choose. This is a good algorithm, but no, unfortunately, it's not going to give me the optimal answer for this problem, because I made this problem more complicated by having some weights associated to the jobs. So it's not only about the how long each job is, there is some actual cost for them as well. For example, you might actually argue that, okay, at the beginning, instead of choosing 12, you could choose 11. The cost of actually the weight of 11 is higher, right? So let's actually think about, review another algorithm. Again, I'm going to start it from the end and choose the latest job which is going to be finished, and always take the one, if there is some tie, I'm going to actually choose the one that has higher weight. So for example, if I'm going to, let me choose another color. Okay, this time, again, I'm going to actually start it from the end, and this time I'm going to, if there is a tie, I'm going to break it by going with the job which has higher weight. So here, I'm going to choose the job 11 instead of 12. And then I can't choose anything else until this point. So it means that I can't choose 10 or 9. It forced me to choose 8. There is no tie to break, so I would take 8. And I cannot take any more job until this point. So until you reach the beginning of 8, right? So it means that I cannot choose 6 or 7. There is a conflict between them, so the next job that I can take is going to be 5. When you reach to this point, when you reach to the beginning of 5, the next job that you can take is going to be 3, and then you can choose 1. Okay, so let's look at the cost associated for these weights that the algorithm gave, these jobs that the algorithm gave me. 7 for the job 11, 7 for the job 8, 4 for job 5, 10 for 3, and 5 for 1. So the summation of all of this is going to be 14, 18, 28, and 32. Interestingly, it actually gives me the same answer as the previous algorithm. It's just, accident. But anyway, this is not going to give me the optimal answer, 36. Okay, so now you can see that the problem cannot be solved using a kind of greedy algorithm. I'm going to talk about greedy algorithm in the next week. But anyway, these two algorithms that I explained to you, both of them were kind of greedy algorithms, because as you can see, at each step, I am just choosing some job and saying that this is the best job that I choose, right? I don't really actually go back and change my choices. That makes it greedy. So, but this problem is more complicated to be solved using a greedy algorithm. The idea that we have to solve this problem is you might actually take some job, but later on notice that this is not good. I'm going to actually change my choice and take something else. For example, when I took 12 here, then after that I took 10. But probably if I actually go and search more, I will notice that this is not a good answer. This is not a good choice. So instead of taking 10, it was better actually to take 9, right? It was, instead of, after you are taking the job 12, you could either actually take 10 or 9. But if you go with 10, you would reach to this answer. So you can see that basically I need to search. I need to exhaustively search all my choices. Okay, so, and whenever I find some answer, I should actually go back and check all other actually possibilities. So this makes it a complete search, an exhaustive search. So it's going to be ideally solved using dynamic programming if I can find some redundancy in the subproblems. So now I'm going to write down that exhaustive search in a more organized way to find out the correct recursion and the subproblems to see if there is any redundancy or no. So the search started from this point that, okay, I have a set of jobs, n jobs. Let's just start it from the first one and say that I am going to take the first one or no. I have two choices, right? So, for example, job 1. You think about job 1. I can take job 1 or no. If I take job 1, it means that this notes that I'm trying to draw are just showing you the search, that this choice is you have already taken one, and this choice is no, you didn't actually take one. So if you take one, it is telling me that all the jobs that have a conflict with one cannot be chosen. After that, the rest of the jobs can be chosen, right? So from this point, at this actually node, it means that I have already taken one, and no, I can't take two. So let's think about the rest of the jobs. The next node, the next job. Do I want to take 3 or no? If I take 3, it will be another node in my search, right? I already have taken 1 and 3, and if I don't take 3, it's going to actually give me another point that I haven't actually chosen 3. At this point, you have two choices again. For example, are you going to take 4? The next job, I'm going to think about the next one. The next one that doesn't have the conflict with 1 is 4. Am I going to take 4 or no? Again, it's going to give me two choices. So just think about this way, that I'm going to choose 4, so it's going to be like I have chosen 1 and 4 so far, or no, I'm not going to choose 4. So in this case, I chose 1, but I haven't actually chose anything yet. So if I'm going to expand this part, it's going to be like I have chose 1, I couldn't choose 2, I didn't choose 3, I didn't choose 4. So for example, at this point, you might actually say that choose 7 or choose 5, doesn't matter. So in that case, let's just go with the numbers. Let's choose 5 or no. So in this case, will be something like, okay, I have chosen 1 and 5, right? Or either I'm not going to choose 5, the next of the options. So let's just expand a couple of some other nodes. This part. So remember, in the first branch, I chose 1. In this branch, I didn't choose 1. So I can choose now 2 or no, right? If I choose 2, this is going to give me another branch in the search space that it's just like I have 2. And or maybe I don't choose 2. Okay, so if you don't take 2, it means that you can take 3. So here I am going to have 2 choices. Either I'm going to take 3 or I'm not going to take 3. And just expand it more. One thing that you might actually notice from these nodes, although they are not very clean, but you should think about is there any redundancy between these nodes in this search tree that I'm drawing? Interestingly, there are some actually redundancies. Look at this case. Here, when I am thinking that I am going to choose 3 or no, I'm not really actually thinking about the rest of it. I'm not going to go back and choose 1. I already have thinking that I didn't choose 1. Okay, so from here, the problem that I'm going to solve is not including 1 and 2. It is telling you that, okay, I have from 3 to the end of the jobs, all of the other jobs except 1 and 2, and I'm going to actually take 3 or no. That's here I actually chose to choose 3 or don't choose 3. This is exactly what happened here, that I already took 1, right? But the smaller subproblem that I'm solving is that is not thinking about 1 or 2. 1 or 2 is out of the problem, and the rest is that I have all the jobs from 3 to the end of the jobs, right? From the job number 3 to the end. So these 2 subproblems are exactly the same. It doesn't matter that I have previously chose 1 or no. It's not going to affect this smaller subproblem. This smaller subproblem is a problem that excluding 1 and 2, but the rest of it is going to be the same. This is exactly the same here, that I'm excluding 1 and 2, and I'm going to solve the rest of the problem. I'm going to get the best out of the rest of the jobs. If you think about it, you can actually have some other redundancies. You can find some other redundancies here as well. So if let me go back to red. After you chose 2, okay, you would say that I cannot take 3. Then my choices is either I would take 4 or no. Okay, so it's going to be, I have already taken 2. I'm going to take 4. Okay, so this node is talking about this fact that I'm going to take 4 or no, and all actually the rest of the jobs. So can you find another job, another node here, which is exactly solving the same problem? If you think about it, let me use another color. This problem that I wanted to solve here is exactly this problem, that I have already excluded 1, 2, and 3, and I'm going to actually take 4 or no. And I don't have 1, 2, 3, and the rest of the jobs remains, and you wanted to find the best answer among the rest of the jobs, excluding 1, 2, and 3. In both cases, in this case and in this case, both of them are the same. So whatever is the best answer for this case is going to be the best answer in this case as well. The difference is that in this node, you are going to later on add 1 to the answer. In this case, you are going to later on add 2. But the subproblem, the smaller problem that you are solving, is exactly the same. So if I find the optimal answer here, I don't need to search here as well. So I found some redundancy in my tree. By storing those redundancies in a table, nicely define the subproblems and store them in a table, I can avoid the redundancy. So let me actually show you a nicer picture. This is exactly, I mean, this tree that I draw here is exactly the tree that we discussed. And the redundancies between the subtrees. If you think about this, the first subtree was that I haven't actually chosen anything. This branch was saying that I chose one, I don't choose one. After choosing one, I choose three, I don't choose three. Choose four, don't choose four. In this case, choose two, don't choose two. Choose four after two, don't choose four. So, and you can find exactly those redundancies that this subtree and this one are exactly the same. Not only that, this subtree, and this subtree are exactly the same. If whatever is the optimal answer you find for that subtree can be used for this case, for this one. So these are the redundancies. So far we have found the redundancies. Now I need to find some way to rewrite the subproblems so that I can store them in a table. And actually I need to figure out that how many subproblems I do have. If it is not polynomial, it's going to be a problem, right? It's not, the result is not going to be a polynomial answer if the number of subproblems that you have is going to be exponential. So far, one thing that we know about these jobs is that, for example, this subproblem that I'm going to solve is telling you that all the jobs except 1, 2, and 3. This is exactly the same as this one. All the jobs without 1, 2, and 3. I'm talking about this subproblem here, not before that. Here you already actually decided about 1, 2, and 3. Okay, you decided about those 3 jobs, you excluded them. So the subproblem here is all the problems except 1, 2, 3. All the problems except 1, 2, 3. Here it is going to be all the problems except 1, 2, 3, and 4. All the jobs except 1, 2, 3, and 4. This one is going to be all the jobs except 1, 2, 3, 4, and 5. Okay, but if I'm going to actually just work on the subset of jobs, the number of subproblems is going to be exponential because you can have 2 power n subset of jobs. But there is a fact about this problem that when you are taking a job, for example, 1, you cannot actually go back in the time, right? If it is going to be the first job that you have taken, all the jobs that has been actually has conflict with that or before that, they're going to be excluded. So if I define some ordering over the jobs, for example, if I ordered all the jobs based on their starting time, it gives me some nice property that if I started from 1 and then I have actually taken 1, then take 2, then take 3. So when you are actually thinking about 3, no other job can be taken, right? Everything to the left of 3 can be actually excluded. This is going to give me some ability to reduce the number of subproblems to linear. So what I'm going to do is I'm going to sort all the jobs based on their starting point. It is going to give me an ordering like this. As you can see, I have ordered all the jobs based on the starting. So it's going to be, the first one is this one that is started at the beginning, then 2, 3, 4. It has changed the order from the beginning order that I had, from the original order that I had. Not only I will order them based on the starting time, I will define, by actually going over all the jobs, I can define some number next of I. What is this next I? It is telling me that for job 1, what is the next closest job that can be taken after you are done with this job, and there is no conflict with that. So as you can see, if you think about taking one, you cannot take two, right? The next closest job that you can take is going to be 3. That's why the next of 1 is 3. What is the next of 2? Next of 2 is going, 3 cannot be taken. Next of 2 is going to be 4. What is the next of 3? For 3 you cannot take 4, you cannot take 5, so next 3 is going to be job 6, right? Or for example, next 4, if you take 4, the next closest job that you can take is going to be, you can take 5, you can take 6, you can take 7, next 4 is going to be 8. Okay, by defining next I mean, I just actually can define next I by going over all the intervals only once. After I sort them based on the starting point, by just going over all the intervals once, you can define all these next I. So now we can actually think about the subproblems that I wanted to define. I am going to actually say that if I chose 1, okay, this a smaller subproblem that I have is going to be all the jobs from next I to the end. So from job 3 to job n, whatever is at end. For example, here is 12. If I take 2, so this subproblem, the smaller subproblem that you would have is going to be from next 2 to the end. Next 2 is 4 to the end. So that variable from next to the end, always end is fixed, right? So the number of subproblems that I have is going to be linear. I only have at most n number of subproblems actually. Okay, so for all of these, if you have n jobs, from job 4 to the end, from job 3 to the end, from job 7 to the end, from job 8 to the end, what is the optimal answer? If I started from job 8 to job 12, if I only consider these jobs, what is the optimal subproblem for, what is the optimal answer for this subproblem, which is covering from job 7 to the end? You can see that that variable that I have is the beginning, from job 7 to the end, from job 6 to the end. So now I can think about writing the recursive relation for my search. I'm going to define this variable opt_i to be the optimal answer, to be the maximum income that we can earn if I wanted to actually solve, if I have only the job I to n. Okay, this problem that I defined, that if I have all the jobs from 7 to n, what is going to be the optimal answer for that? I'm going to show it by opt7. If I am going to consider all the jobs from 6 to 12, what is the optimal answer? I will save it somewhere like opt of 6. Okay, so if I mean, I have designed I have defined this variable, what is going to be the optimal answer for the original problem? This is going to be opt of 1, right? It is telling you that what is going to be the optimal answer if I have all the jobs from 1 to n. This is going to be stored in opt1. So now I need to write down the recursive relation for generally for opt_i. So if I, let me use under color black. So if you think about this recursive relation, if I'm solving a problem like what is opt of I, it means that you are at some point and you wanted to actually just say that from, for example, 5 to the end, what is the optimal answer? It is exactly the first recursive tree that we, exhaustive search that we think about. Either you are going to take job 5 or no. If you take job 5, the rest of the problem will be from the next of 5, right? From job 9 to the end. Okay, so you have two choices for opt I. Either you take the job I, so whatever is the weight of I, you are going to take it, plus whatever is the optimal answer for all the jobs that can be actually, the job that you can, there is no conflict with that and I. What is the closest one? It is coming in the next I. So now you see that why I have defined it that next I. Next I is going to help me to say that if I take 5, the next closest job that I can take is going to be 9, right? So I would immediately discard 6, 7, and 8. And I'm not going to actually think about the rest of them. So it's going to be this subproblem that from 9 to 12, what is going to be the optimal answer? Whatever is the optimal answer, you add it to WI and it's going to be one answer for you. And the other choice is that you are not going to take job I. So if I'm going to actually solve this problem that includes all the jobs from 5 to the end, I have two choices. Either take 5 or don't take 5. If I don't take 5, the answer that I would have is I can take the next job. The next job is going to be the next job is going to be I plus 1, right? So whatever is the optimal answer from 6 to the end. I just need to compare between these two. If this is larger, you take this one. If this is larger, you are going to take this one. Just simply, I am either going to take I, or I'm not going to take the job I, or I'm not going to take the job I. So this is going to be the final recursive relation. These are those two options that I mentioned. This is going to be the general formula for I, right? You either take job I or you are not going to take it. If you don't take I, you can simply just go and take the next job, right? So from the next job to the end. And what are the base cases? The base case is that if the value of I, if the job that, the set of jobs that you are actually taking is 0, if there is no job remain, right? If there is no job remain, so opt I is going to be 0. You can just think about it as the optimal answer. So that's why I wrote this one as for all value of I greater than n, because we started from the beginning to the end. So if I is greater than n, it means that there's nothing remains to choose. So if I want to define this write down this recursive algorithm in a form of a complete pseudocode, it will be something like this, that you sort all the jobs first based on their starting time. You calculate the next of I for all the jobs after you sort them. And then I'm going to actually create this array to keep the solution for all subproblems. For the subproblem, you can see that I've started from 1 until n plus 1, and n plus 1 is going to actually keeping that base case, that of course from job n plus 1 to n, it means that there is nothing remain. So I'm going to define it as 0. It's just an initialization for the base case. And I didn't actually write this one in a recursive form. It is very clear that we can basically just write it in an iterative way, and it's going to be written in this. I'm actually filling this table, but starting from this is, let's just call it opt, right? And this is going to be, for example, n plus 1, whatever index n plus 1 is going to be index n, and I'm filling this table from the end until I reach to this point, because this is going to be the largest problem that I have, and these are the smallest. I mean, intuitively you usually actually fill the table from the left to right, but in this case, because the subproblems that I have are going to be smaller if the index is bigger, so this is going to be corresponding to the problem of only having one job, the last job, when you sorted them. This is going to be the only having the last 2 jobs, only having the last 3 jobs. Okay, so I'm going to fill this table from here. You fill this one first, then this part will be filled, this one. And you can see that whenever I'm filling opt I, in this loop is actually iterating from the end, from n to 1, and when you are filling this one, you are using I plus 1 and the opt of next I, which is definitely going to be greater than I, right? So when you are, for example, filling something here, you are using the solution from 2 other subproblems here, from this one, sorry, and somewhere else, which is going to be the next I. So what is the time complexity of this algorithm? Sorting the jobs based on the starting point is going to be n log n. Calculating next for all the jobs can be done in linear time. If you this is going to be a nice algorithm if you are not getting it immediately. Think about it, that if I already have all the jobs sorted, I can start it from the first job and calculate next for all the jobs by just iterating over the jobs only once. I mean, this is going to be a very nice algorithm. If you didn't get it, email me. We can actually talk about it. After you calculate it, next, so here it's constant, and I have a loop here, and the loop is going to be O of n because the cost of each iteration is constant, right? I'm just checking 2 subproblems, this subproblem and this subproblem, and getting the max. So in total, the time complexity is going to be n log n, the cost of sorting them at the beginning. So now you can see that something that at the very first it looks very complicated, something that we felt like it's going to be an exhaustive search, when we rewrite it, when we try to actually find that recursive relation and find the subproblems, find the redundancy between subproblems, it's basically very simple. Even if you wanted to actually write down the code for this, it is very simple. So this algorithm that I wrote here only find actually the optimal cost. Okay, so you need to modify this to give you that set of job that you want to choose. Just take it as an exercise. How can I modify this algorithm to not only calculate the income, the maximum income that I can get, but also give me the set of jobs. It's going to be just some simple modification over the algorithm. You need to keep another array to keep and mark all of those jobs that you are going to choose. This actually, I have already actually talked about this, that why I have ordered the job based on their starting point. Basically, the reason was that if you don't have some ordering for the jobs, when you are thinking about a subproblem can be any subset of the jobs, right? And we don't want that to be the subproblem, because we are going to have 2 power n different subproblems in that case. Although we don't really need that many subproblems. When we are ordering them, we are actually reducing the number of subproblems.